This is the formal description of the stack machines as we talked about last time. I just want to remind you how the delta works. This, these formal descriptions, we usually don't use them, but this is how the delta works. All right. We decided we would all stand up when you got here. That was pretty awesome. All right. What I said at the very end last time, I would like to do a real definition of, formally speaking, what does this mean? All right, from a formal description, can we say what exactly that arrow means? So, for instance, in this example, you can do that arrow. For example, if I had something like ABA, comma, S11. You can do that arrow, and it would become BAS111. So in that particular version of the arrow, what I did was rule number 1 here. If I were to give them numbers, which you don't have to give them numbers every time, but what I did there is rule number 1, where I read A, pop the S, and push S1. That's why the A here disappeared, and this string was ABA. It's now BA because I read the A. And then we did pop S and push S1, which is this S here was replaced by S1 over here, all right? But that little arrow there is actually, in sort of discrete math terminology, it is a relation. That is, sometimes you are allowed to write something with the arrow and something else, but you have to do it right. So what exactly counts as doing it right is what I want to talk about here. According to that delta, the delta has all those values. This arrow here has something to do with delta. So when is it legal or correct to write? Should we stand up again? When is it legal to write something like, AX, comma, I don't know. I just mean, when is it legal to write something like some stuff, comma, some stuff, and then the arrow, and then some other stuff? In terms of the read, pop, push, which is another way of saying in terms of the delta. When are we actually allowed to do that? All right? And the answer is kind of technical and maybe confusing looking on its surface, but I'm going to try to explain what it means. So when we have some particular row of the stack machine, when we have a rule like, read A, pop, let's say B, push Y, maybe. I'm trying to give some generic letters for the whole rule. When we have a rule like that, another way of writing this in the super formal description, it would mean that Y is one of the things in delta of A comma B. Remember, the delta, its answer is always a set. See up there, those deltas. The answer is always a set. So when you have some element of this set, it means that there is a rule like this. Read A, pop B, push Y. And what does that mean in terms of what kind of little arrow things are you allowed to do then? So then, when we have a rule like that, then we can write with an arrow things like, if I had a string which began with an A, and then after the A was some other stuff, it doesn't matter, I'll say X. And then another stack string where on the top of the stack was a B, and then after the B was some other stuff, maybe Z. Then it becomes, can anybody say, what will that become if I do read A, pop B, push Y? X, Y, Z, yeah, isn't that cute? I arranged it so that would work out like that, right? If you have ax comma bz, and you do that rule, read a, that means you throw the a away, and what remains from the first part is just x. And then for the second part, you get rid of this b and replace it with y. And that's why it says x comma yz. All right? So this is a very convoluted, but there's no better way to write this really. That's the definition of what this arrow means. If you see an arrow in this kind of scenario, it means apparently there was a rule that says you can pop a, you can read a, you can pop b, and you can push y. Right? That's what the little arrow means. So when we have a rule like this, then we can write this. There is no simpler way to say what exactly the arrow means. It just means in a scenario like this, you popped the A, you read the A, you popped the B, you pushed the Y. All right? When we use the arrow, remember the arrow indicates one step, doing one of the stack rules. For these pairs are called, remember each of these pairs, these are called IDs. Instantaneous descriptions is what the ID stands for. We also are going to write something like x, y. As usual, when I put the star, that indicates several iterations. So when I say x, y, and then the arrow with the star goes to zw, that means it doesn't necessarily happen in one step, but if you do many, many different arrows, you can eventually get to zw. So we also write this when x, y can become zw after several steps. They don't have to be the same step, just several different stack rules, all right? And now, given that we have that symbol, we can write down, formally speaking, what is the language of the stack machine. So then the language of the stack machine, the language accepted by the machine, the language of the stack machine. This is the actual definition. I'll write L of M. M is the stack machine. It is the set of all. It's the set of all strings for which something or other is true. I'll say X in sigma star. That's the string alphabet, the input alphabet. Anything you can say? What does it mean to be accepted on a stack machine? You could say in words first and then try and write it as symbols. Can you remember in words just what it means to be accepted on a stack machine? You start from something, you do a bunch of stuff, and you end up with something. Empty. You end up with empty everything, right? You read the whole string, and it ends up with empty string on the stack. I want to write that over here as you start with something, and then use this guy right here, right? And eventually it becomes something else. That's what you want to say. So what do I start with? And then it ends up being something else. So she said it ends up being empty. I think more specifically, it ends up being this, right? You read the whole string, so the input becomes empty, and the stack also becomes empty. And where do you start in the stack machine? Yeah. X, comma, S. Great. You always start with your string, comma, the starting symbol, S. This is the formal definition of the language of the stack machine as a set. It is all strings in the input alphabet, that's here, such that if you start with X, comma, S, do the steps, eventually you can make it down to empty, comma, empty. That's the definition. So if you ever really want to prove things about a stack machine, this is really the way to go about it, although I don't think we're going to do any examples. It's a little complicated. Just because this arrow, the technical definition of this arrow is quite complicated, right? It's all this stuff basically, which is kind of a pain to work with. But in theory, if you wanted to write proofs about stack machines, you would use this definition of the language. All right, great. I want to talk about a few things. So I would consider this the end of our sort of introduction to stack machines. What I want to talk about for the rest of today and probably tomorrow also, and maybe a little more after that, is what kinds of languages are accepted by stack machines? What kinds of languages? Can we accept with stack machines? For instance, can you make a stack machine for any regular language? I don't know what your intuition about that is, although we have seen already there are some non-regular languages that have a stack machine, like A to the n, B to the n has a stack machine, and that's not regular. So the stack machines, certainly they don't only do regular languages, they can do some other things. But this is the kind of questions that I want to talk about. Regular, other categories of regular. I mean, there's also non-regular, but that's an enormous category. We've also talked about context-free languages. Those are the ones which you can make with a context-free grammar. Can you do any of those on a stack machine? Like A to the n, B to the n, it's not regular, but it is context-free. And you can do that on a stack machine. So this is the kind of questions. What this would involve, another equivalent way to ask these questions, equivalently, can we convert NFA to a stack machine, right? Because if that was true, then automatically that means any regular language you can do in a stack machine, because NFAs can make any regular language. And if any NFA could be converted to a stack machine, then you can automatically get regular languages. And then you could also ask, can we convert, say, a context-free grammar into a stack machine, right? If that were true, then you could get any context-free language on a stack machine. So these kinds of conversions is what we want to talk about. I'm not saying these are always possible to do, but that's where we're going with this. Converting stack machine to NFA, or the other way around, converting NFA to stack machine, and similarly for context-free grammars. All right. And this, by the way, is what I said might actually help you out on this homework and also on our test. In my opinion, writing a stack machine to do a particular thing is quite difficult sometimes, and it's hard to think it through. But if there were some kind of way to do this kind of conversion, it means if I ever ask you to make a stack machine that does whatever, you could instead make an NFA and then convert it to a stack machine. Or if that second one is possible, you could make a context-free grammar and convert it to a stack machine, which in my opinion is easier to do than creating the stack machine by hand. So these are going to be, I mean, they are theoretically interesting conversions, but also useful just because, in my opinion, making a stack machine from scratch is often difficult. Let's talk about NFAs first. Actually, this is something that we talked about once before, although I didn't make a big deal of it at the time. But let me just say, we can convert any NFA to a stack machine. This automatically means, so any regular language can be done on a stack machine. Just because any regular language can be done on an NFA, and then you can convert it to a stack machine if you want to. All right. And how to do this? You know, you have to think about the fact that an NFA, we think of the stack machine as a machine which has a certain type of memory. It can remember things in a stack, right? The NFA, though, let's just do an example. I will draw an NFA here. I'm going to have 4 states, S, T, Q, R. And let's go like this, A, B here, A. Let's put an epsilon in there just to make it interesting. All right, how about this NFA? As you are reading a string on a stack machine, it is allowed to keep track of the entire stack, which can grow quite big and shrink down again by the time you get to the end. On an NFA, though, all you have to keep track of from one step to the next is which state you're in, right? That's like the NFA only has these 4 possible memory configurations. And we can just build a stack machine which stores the state on the stack, and the stack never grows. It only just ever contains one letter on it, which tells you what state you're in as you're reading the string. So we can build a stack machine which remembers the state. So in this very particular type of stack machine, I'm never going to make the stack any bigger than just a single letter. It will always just keep track of what state we're in. So for example, and then, I mean, with this general idea, I think it becomes clear what the rules should look like. Read, pop, push. For example, if I read A and I'm in state S, you have to think of that as popping the S. If you're in state S and you see an A, according to the NFA, you should read that A and then change the state to T. And since I'm storing the state on the stack, that rule looks like that. Pop S, push T. What this represents is if I'm already in state S and I read an A, I should get rid of that state S and replace it with a T, right? And then just basically every arrow that you see up there translates into a different stack rule. Now actually this is not the only arrow from S with an A. SA also goes to Q, so that becomes another rule. Read A, pop S, push Q, right? Because you can also change the state from S to Q reading A. And then, all those other arrows need to be translated into lines of my stack machine. So I see, for example, an arrow from T to Q with a B. That looks like read B, pop T, push Q. I see the other A arrow from R up to T is a read A, pop R, push T. And then the epsilon line. You don't get too fancy about this. It just translates in the same way. If I'm in state Q, I can go to R without reading anything. That's a read epsilon, pop Q, push R. Right? This is how we convert an NFA to a stack machine. It's quite simple. There's one piece of information on the NFA which I've not yet really represented on the stack machine. Anybody know what I'm thinking? Yeah, the accepting state. So how do we indicate that R is supposed to be accepting? It means basically, any ideas? Yeah.
Read epsilon, pop R, read epsilon.
Yeah, read epsilon, pop R, push epsilon. Sorry, I went over the page break here. I'm just gonna do one of those. Great. This means if you really do get all the way down to the last, the end of the string, and you're in state R, it should be accepted. And in order to be accepted on the stack machine, you need to get down to a clear stack. So this will clear out the stack at the very end. All right. So to summarize, this is very easy to do. Any arrow that looks like X, A, Y like this becomes a rule. Read A, pop X, push Y. That's all there is to it, really. And any accepting state, if you have an accepting state, say called Z, becomes epsilon, Z, epsilon. If you have more than one accepting state, you put more than one rule that looks like that. And that's really all there is to it. Let's just do a quick example derivation in this example. I'm going to have to shrink it a little bit, or maybe I'll just copy this. So a quick example, let's on my stack machine show a derivation for that accepts, how about AB? AB is accepted. because on the NFA I can start here and do A, then B, then epsilon, right? So A, B is accepted. Can I write a stack derivation using our rules there for A, B? You got to start A, B, comma, S, and then I want to do rules to get down to epsilon, comma, epsilon. How do you decide which rules to use? Well, basically, you decide what you would do on the diagram, and you do those same rules in that same order. So on the diagram, I start in S, and I would do A first over to T. And so that's the first rule I'm going to use, which is read A, pop S, push T. So it becomes now BT. Next on the diagram, I would do that B edge, the diagonal one. So I do the corresponding stack rule, which is BTQ. Oh, this one here. Read B, pop T, push Q. So it's going to go to now epsilon Q, right? And then finally on the NFA, the next step I would do would be Q to R, the epsilon transition. That would be epsilon QR, which just turns it into epsilon comma R. And then I'm in the accepting state to actually finish the stack computation. You do that final rule, epsilon R epsilon, turns it into epsilon epsilon. There you go. So to make your derivation, you just follow the same steps that you would have followed on the NFA diagram. Any thoughts about this one? I think this is actually pretty straightforward procedure to do. So the moral of the story, and you can use this on your homework, maybe, I think so, and you can use it on the exam this week. If I ask you to make a stack machine for a regular language, it may be easier to draw an NFA and then convert it. This is a very simple conversion, right? Some of our conversions are complicated, but this is not complicated. So that's my it's a little life hack for you, all right? Can we try one? I want you guys to try one. It's not hard to do. Let's try convert this NFA into a stack machine. Now, I am not going to name the states. You're going to have to name the states when you convert it into a stack machine. But convert to a stack machine. And let's do a show a derivation for ABAAB on your stack machine. All right, see what you think. Yes?
What letter from the starting state to?
Oh, yeah, I didn't put anything there. All right. How about A? Thanks. I'll give you a moment. I'll walk around and see how you're doing. You don't have to think too much. You just do the procedure that I described. You can name the states whatever you want, but I see most of you have realized you better name the first one S, because that's what the stack machine is supposed to start in. All right, I'm going to try and do this real quick, and then we'll talk a little bit about grammars. I'll call them S, X, and Y, which I don't know if any of you did that. Okay, I started by writing read S, which is wrong. It's read A, S, X. All right, I had 7 lines in my stack machine, 7 rules, which is, I hope, what you also had. Don't forget the epsilon S epsilon should be the very last one to indicate the accepting state for the stack machine. And then my derivation, A, B, comma, S. I'm going to look at the NFA and decide what I would have done. I would have gone up to X first. So first I'll go B, comma, X. And then I would do the looped edge on X, so it will stay as X. Then I would go down the edge for A to Y, so this would become A, B, Y. Then I would do the looped edge of the B there, it would become A, Y. Then I would go across to S again, it would become epsilon S. And then finally the last rule gives me epsilon, epsilon. I hope you wrote something like that. All right. Pretty. It works out pretty nicely to do this kind of conversion. Yes.
How did you get rid of that last B before the I? Like where it's.
Oh, yeah. Sorry, I did it wrong. I was just about to say how easy it is, but I did it wrong. A, B, Y. You read the A. I read the B for some reason. But you read the A and it becomes BS here. And then epsilon S, and then epsilon, epsilon. All right, thank you for that. All right, so if I were to summarize this procedure as a procedure, it works the way that we said, but it gives you kind of a theorem for free. It says if L is a regular language, then there is a stack machine accepting L. All right. I'm going to do a similar trick for grammars, for context-free grammars. And this one is actually very powerful and will help you to do many of the homework problems if you want to do it this way. Make it grammar. Can we convert a grammar, context-free grammar, to a stack machine? Actually, we can. So I'll just say we can also convert context-free grammar to a stack machine. This, in my opinion, is very useful because I personally find it a lot easier to make a context-free grammar for something than a stack machine. And if you ask me to make a stack machine for something, unless it's a very easy example, I will usually try to make a grammar and convert it to a stack machine. And the conversion process is not hard to do. Anyway, I thought we'd just do a particular example. Here is a context-free grammar. S goes to ABSA or T. T goes to BT or epsilon. All right. The language of this, I suppose, this would make a nice little test question. Tell me what the language of that is. Anyone want to see what you think? I'll write it as a set. The language is, yeah?
Is it A, B to the N, B to the M, A to the N?
Uh-huh, yeah, I like that. Yes, when I see this kind of action, this makes me think ABs are being balanced with A at the end. So ABs, there's some number of ABs at the beginning, followed by, and it has that same number of A's on the end. And then what about in the middle? In the middle is this t thing, which the t represents any number of b's. So yeah, that's great. All right, anyway, that's not important though. I want to convert the grammar directly into a stack machine. Here's my strategy for derivations, and then I'm going to try to convert that into a stack rules. Strategy for derivations. If I want to derive a string in this language, let's say A, B, B, A, all right? What you see here is A, B, balanced with A, right? And then in the middle, a bunch of extra B's. So that's part of this language. Here's my strategy. You know, this derivation, it must begin like this. My whole string, comma s, that's where the derivation starts, all right? But I'm going to think about how would I have derived that string using the grammar? The first part of the grammar is s goes to a, b, s, a, right? So that's what I'm going to do for my first step. A, b, I'm leaving the string the same. B, 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 a, comma, a, b, s, a. So what I just did there is actually an epsilon transition in the stack machine because I didn't read anything from the input, but I just changed the s into a, b, s, a. But in terms of the grammar, the way you think of this grammar is like s is basically the same as a, b, s, a, or it is possible, it is allowable whenever you want to change s into a, b, s, a. So this is an epsilon transition that I just used there. And now the strategy is when I see A and B on the front of the stack, they match with A and the B on the front of the input, and I'm going to pop them off. So I'm going to read this A and destroy that A, and then read this B and destroy that B at the same time. So here I read the first A, B, A, B, 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 A, and I pop the A off the stack, and it says B, S, A. And then I'm going to do the same with the next B. I read the B off of the input string and pop the B off the stack. I'm going to just keep on sort of canceling letters. Oops, it doesn't start with a B anymore. Now it starts with A. And then B, 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 A, comma, S, A. All right? And now I have another grammar non-terminal symbol, and I can decide now what that S should turn into in order to continue my derivation, all right? Thus far in the derivation, you might feel like what we've done so far is sort of canceled off those first two letters, right? That A and that B. And so now, according to the grammar derivation, I need to think about how exactly do I produce the next letters, A, B, and they are by doing this same grammar step again. And so I am again going to change this S to ABSA and not using any of the input. This is another epsilon rule. So the string will be the same, A, B, 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 A, and now S becomes ABSA. But then there was an A at the end also. All right? Again, I do two more rules to cancel the A on the front of each, on the front of the input and on the front of the stack. Canceling the A gives me B, 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 A, comma, B, S, A. And then canceling the B on the front of the stack and the front of the input gives me B, 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 A, comma, S, A. Yes?
Well, you read the A, or wait, why don't you like also get rid of the SA? Like you're just getting rid of the S. In one of the steps, right, and then you add the A, B, S, A. Why don't you get rid of both the A and the S versus just the S?
Yeah. Since I'm doing stack operations, I have to pop one thing at a time.
Oh, okay.
Yeah, you can't actually. And really, this A represents the A on the end, which represents this A in the input, which I haven't got to yet. So I don't want to cancel that A until the very end. All right. What am I going to do next? Now I have to start, the next thing I'm going to be canceling is this B. So at this point I'm kind of like here now. and I next need to cancel this b. An idea, yeah?
So you could do the T.
Yeah, in terms of the grammar, what I want to do next is this s becomes t, and then that t becomes bt. Actually, that would happen 3 times. So next, I'm going to do another rule which changes the s into a t. So it'll be BBBAA and then TAA. And then that t should become BT. So this is BBBAA, BTAA. And then I can cancel a b from the input with the b on the stack. Then it looks like BBAA. Are we almost done here? I think so. We're getting somewhere. BBAA, TAA. I have 2 more b's to cancel, so I'm going to do 2 more times of that t goes to bt stack grammar rule. So this becomes BBAA, BTAA. Then cancel the b's, BAA, TAA, right? We're getting somewhere here. Again, t goes to bt. Lets me do BAA, BTAA. Canceling b's, I get AA, comma, TAA. Anybody see how to finish this off? Yeah? Yeah, I go t goes to epsilon, gets rid of the t entirely, and I just have AA and AA, and then I just cancel the a's with one another. So one step makes it AA, and the last step makes it epsilon, epsilon. All right? So long derivation, but there's basically 2 kinds of rules that I was using. One was rules corresponding to the grammar steps. I'm trying to let you see the whole thing at once. Rules corresponding to the grammar steps are epsilon transitions in the stack machine. Read epsilon, pop something, push something, right? And then there were the rules of canceling the letters. You cancel an A with an A on top of the stack, or cancel a B with a B on top of the stack. All right? Those are all the rules. So basically, if we have, I'm going to try and summarize, any grammar rule, like, X goes to Z, makes a stack rule, read, pop, push. These grammar rules make epsilon transitions in the stack. So they are read epsilon, pop X, push Z. If you have a grammar rule like X goes to Z, read epsilon, pop X, push Z. That's how you translate all the grammar rules. And then you also have the letter canceling rules. And then I'll just say plus rules like A, epsilon. This is canceling A's. You can cancel A from the input, cancels the A on the stack, and you push epsilon because you're canceling, you're not replacing with something else. And then B, epsilon, etc. If there are other letters, you would do C, epsilon, that kind of thing. All right? This is the entire procedure for converting context-free grammar to a stack machine. Yeah?
What exactly do those, where do those bottom 2 sort of come into play, I guess?
They were, I used them often in this derivation here. For example, like right here, BAA, BTAA. I said, now I cancel the B's, and I end up with this. That canceling of the B's is actually this rule here. Read B, pop B, push epsilon. So that's why you need them.
So is the first rule just for changing the where you are, so the direction?
This one you mean?
Yeah.
Yeah, this is for doing the actual grammar steps, like T goes to BT or something like that. So that was what we did here. This T became BT. It was a read epsilon because the input string stayed the same. Pop X, push Z. All right? This is the procedure for converting context-free to a stack machine. Why is it important that this be context-free? This only works for a context-free. Anybody see why? It is necessary that the grammar be context-free. First of all, does anybody remember what context-free means? Yeah?
So like there's not like an A before the X?
Yeah, for instance, like right here, it means the left side of the arrow is a single non-terminal symbol, just one letter on the left side of the arrow, all right? And why then does this procedure, this conversion only work if it's context-free? Yeah?
Because we can only pop single.
Yeah. It's because we translated this rule putting X right here. And remember, when in a stack machine, you're only allowed to pop a single letter at a time. So the fact that this X goes there, this will not work unless the X is a single letter. So X must be a single letter since we did something like pop X, right? This is why it won't work on a context-free grammar. And in fact, there are some context-free grammars which cannot be written as a stack machine. But any context-free grammar you can write as a stack machine. Let's just do, we got 5 minutes here. Let's just do a real simple example. How about everybody's favorite non-regular language, A to the N, B to the N? How would we do this on a stack machine? I mean, we've done this example already, but it might be interesting to see just how it works out. S goes to ASB or epsilon, right? That's the grammar that you would use for this. So this is a context-free grammar. And then as a stack machine, it looks like read, pop, push. Every grammar transition becomes this kind of epsilon, right? Read epsilon, pop X, push Z. So this becomes the first one there, epsilon S ASB, right? This is the one that said S goes to ASB. And then there's also the one with the epsilon. S goes to epsilon. That would be written epsilon S epsilon, right? That comes from S goes to epsilon. So when you see the bar there, you have to consider that as two separate grammar productions. And then we also need those other two letter canceling rules. A epsilon, B epsilon. And that's it. So this is a stack machine for A to the N, B to the N. Although it's different from the one that we saw in class, an example for a stack machine, A to the N, B to the N. But this certainly works. Yeah?
So the only things that really change are like the epsilon rules, but then like other than that, like based on whatever your alphabet is, you're gonna have letter canceling rules for all the letters.
Yeah, that's right. So every grammar rule turns into one of these, and then you always just put these letter canceling rules for every letter in your alphabet. And that's all there is to it. Yes?
Can we maybe do a derivation for this?
Yeah, sure. Let's try to derive. How about derive AABB? Great idea. What you want to do is think about how would you have made that on the grammar, and then try to mimic those grammar steps on the stack machine. Maybe I'll just write first of all the grammar derivation, and then we'll try and copy the grammar steps onto stack derivations. So this is in the context-free grammar. To derive AABB, I start with S. This maybe is why our book uses different arrow styles. This is the grammar derivation, right? Those are the grammar steps that I would do to derive AABB. What are the stack steps? Well, you do those same grammar steps in that same order, only you also cancel letters as you go whenever appropriate. So on the stack machine, I begin with AABB, S. And I'm going to do the first grammar step, S goes to ASB. In the stack machine, that's the first rule, which is read epsilon, pop S, push ASB. So my input stays the same, AABB. I pop S and replace it with ASB. So now this says ASB. All right, that was the first grammar step. So that's really, these two arrows are kind of representing the same step. Now I'm going to do some letter clearing. I have A on the top of the input and also A on the top of the stack, so I'm going to cancel those using the first of those letter canceling rules. It will say ABB, comma, SB. All right. What should I do next for the next stack step? I've canceled all the letters that I can. So then next I'm going to do one of the real rules.
S to S.
Yeah, the grammar step would be S goes to ASB. I'm going to do the corresponding stack step, which is read epsilon, pop S, push ASB. So this now becomes ABB, comma, ASB, ASBB, like that. This is really that second grammar step is happening right now on the stack. Then we do some more letter canceling. The A's on the front can cancel each other. I get BB, comma, SBB. And now I throw away the S, and we do have the rule you can see at the very top right now. Epsilon S epsilon allows you to discard the S. So I go S goes to epsilon, leaves me with BB, comma, BB. And then those you cancel letters one at a time, and you end up with B, comma, B. Finally, epsilon, comma, epsilon. All right. You may find on the homework this is an easier way to do some of those problems. Make a grammar first and then convert to a stack machine. All right, time to go. See you tomorrow. Bring your questions for the test. I would be happy to go over stuff if you want to.